Let us now go ahead with the discussion of single phase induction machine. Till now we have discussed 3-phase induction machine and we used a 3-phase stator winding. We passed a 3-phase balanced current through the 3-phase stator winding, which resulted in a rotating magnetic field. Now because of this rotating magnetic field, the electromechanical conversion was possible in 3-phase induction motor. But what happens in a single phase induction motor? There will be no rotating magnetic field. The magnetic vector will point in one direction only, and in this direction the magnitude, that means the length of this vector, this will keep changing sinusoidally, okay, like this. But the vector itself, it is always pointed in one single direction. You have to understand that current will be induced, transformer action will take place. That means if this is the stator winding, you can represent it in terms of a single phase transformer. If this is the stator winding, a single phase AC signal is passed, then this will introduce or induce the current in rotor winding. So this will be short circuited, right? Rotor windings are short circuited. So this is how single phase induction motor is going to look like, just a stationary single phase transformer. Therefore, magnetic induction is happening but torque is not produced, okay. But this is the problem with starting only. Once we somehow start rotating the induction motor, then it has no problem in continuing to keep rotating. That means the torque will be induced once it starts rotating, okay. So why induced torque will be produced after it starts rotating? There are two theories for it. First, you can write down, once the rotor begins to rotate, an induced torque will be produced in it, okay. So why it will be produced? There are two theories to help explain this. One is called as the double revolving field theory and other is the cross field theory. So we will see both of them one by one. What was the first one? Double revolving field theory. So here what is going to happen? The single magnetic field vector that you have, this we can resolve into two vectors such that the two vectors are rotating in the opposite direction. So that means if this is the magnetic vector and this is given by Bm sin omega t I cap, right? Bm sin omega t is the magnitude and the direction is always in the I cap direction, that means in the x axis, horizontal, right? Bm is the maximum value. Let us now take one vector here and another vector will be like this, right? So that when you are adding these two vectors, you are going to get the original vector, okay. So let us say this is moving in this direction and this is moving in the opposite direction. So this we will take as the clockwise vector and this we will take as the counterclockwise vector. So how can we represent them? The clockwise vector we can express as half Bm sin omega t I cap minus half Bm cos omega t j cap, and the counterclockwise vector you can express as half Bm sin omega t I cap plus 1 by 2 Bm cos omega t j cap. Now what will you get when you add these two vectors? This and this will be cancelled and this addition will give you Bm sin omega t I cap, the original vector. Now if you take at any time instant t is equal to 0, let us say, what will be the clockwise vector where it will be sin omega t will be 0. So you are going to get minus 1 by 2 Bm j cap. And where will the counterclockwise vector be? this is going to be at 1 by 2 Bm J cap. So when you add both of them, they will get cancelled out. So you're going to get 0. The same thing is going to happen when you substitute T is equal to 0 here. The magnetic field vector, you're going to get 0. So in this way you can verify at various time instants, you can check and you can verify that when you add both of them, this will result in this vector. Okay. Now what is the advantage of this? You can see that this clockwise and counterclockwise vectors, they are now rotating fields. This B bar may be stationary, but these two are rotating fields, and at any instant of time, when let us say when this is here and when this is here, when you add up, it is going to give B bar. And further, if they are going, let us say this vector is coming here, the counterclockwise vector, and this clockwise vector is coming here, then also if you add, then you are going to get the B bar. Now how can you say that this is not rotating while these are rotating? You can see from the expressions. The magnitude is changing with respect to time, but the direction is always remaining as I. Whereas if you see this clockwise vector, what will be the magnitude? Mod clockwise vector is equal to root over half Bm square, you can take out common, into sin square omega t plus cos square omega t. You are going to get 1. So this will be Bm by 2. What will be the phase of the clockwise vector? This is equal to minus tan inverse cos omega t divided by sin omega t. So that means the magnitude is now remaining constant, whereas the angle is changing with respect to time. Similarly, you can do similar calculations for this. The magnitude, you are going to get a constant, which is again Bm by 2, and the angle, you are going to get time varying angle, tan inverse cos omega t divided by sin omega t. So these two are rotating vectors, whereas the original vector is not a rotating vector. So we have established sum of two rotating vectors, that is BCW and BCCW. This will give you a non-rotating vector. Okay. So we have resolved the magnetic field vector, the non-rotating magnetic field vector, into two rotating vectors. Now we can draw the torque slip characteristics for each of the rotating magnetic fields, right? So this is the torque, let us say, and this is the speed axis. So one of the field, either the clockwise or the counterclockwise, you are taking, then it is going to be something like this, right? Now the other field, which is in the opposite direction, it will be a mirror image with respect to the vertical axis. Why is that? Because here we have positive speed, and if the magnetic field vector is in the opposite direction, then the speed will be in the opposite sense we can take. Okay. So in that sense, we can draw starting from here, it will go like this, reach a peak, and then it will fall again, right? Now what will be the speed values here? This is going to be plus ns synchronous speed, this is going to be minus ns. Okay. Now this value is going to be equal to this value, because these both are essentially the mirror images of each other with respect to the vertical axis. Okay. So now the torque slip, because of both these vectors, what will it be? It will be roughly equal to the sum of this. See, remember, we are adding this B bar is equal to these two vectors, sum of these two vectors, but it does not mean that the torque slip characteristics we can simply add. Okay, but it will give you an approximate value, and from that approximate value you can see that since this torque and this torque, they are equal here, the resulting torque will be 0 at 0 speed. Okay, so you are going to get something like this. This is the approximate torque slip characteristics of single phase induction motor. Okay, and from these characteristics you can see that at 0 speed the induced torque will be 0. That is why the induction, single phase induction motor, it cannot start on its own. But once there is rotation, there is going to be an induced torque. Okay. So this is one theory which explains why there will be an induced torque when the motor starts running. What is the next theory that we have? Cross field theory. So here we anyways know that there will be a stator magnetic field as well as a rotor magnetic field. Okay. Now the only problem is they are not rotating. They are pointing out only in a certain direction. What is the only thing that is changing? Their magnitude is changing. Okay. They have a pulsating magnitude. Now what happens at near synchronous speed? So that means using some means, if we are able to rotate the machine, the single phase induction machine at near to synchronous speed, not synchronous speed but near to synchronous speed, if we are making it rotate, then the stator magnetic field, if we are taking as Bs bar, and the rotor magnetic field, if you are taking as Br bar, then Bs bar and Br bar will have 90 degrees phase difference, both with respect to time as well as with respect to space. Why it is with respect to time? We know anyways, because the rotor circuit is predominantly reactive. So the current will be 90 degrees lagging with respect to voltage. So accordingly the magnetic field vectors also will be lagging with respect to time by 90 degrees. But why space? This is happening because the motor is running at near synchronous speed. This 90 degrees of phase difference with respect to time will also reflect in terms of space only because they are moving at synchronous speed. Okay. So now when you have two vectors which have a phase difference of 90 degrees both with respect to time and space, you can get a rotating magnetic field. Okay. So how is that? You can see if Bs you are taking as some magnitude Bm sine omega t at an angle 0, and rotor magnetic field, if you are taking Bm, how will you represent time difference? Sine omega t minus 90 degrees at an angle of 90 degrees, minus 90 degrees, because we are taking this as 0. Now what will happen when you add both of them? This is going to be Bm sine omega t minus j Bm sine omega t minus 90 degrees. Okay, because this angle minus 90 degrees is nothing but minus j. Now what is sine omega t minus 90 degrees? It is minus cos omega t. So you are going to get Bm sine omega t, minus and minus will become plus, so plus j Bm cos omega t. So what will be the magnitude of this phasor? This is going to be Bm root over sine square omega t plus cos square omega t. You will get 1. So Bm will be the magnitude, and what will be the phase? Tan inverse cos omega t divided by sine omega t. So we have a constant magnitude, whereas the phase is changing with respect to time. So that is how even if you have two vectors which have a 90 degrees phase difference with respect to both the time and space, both should be present, then also it is possible to get a rotating magnetic field. Now once there is a rotating magnetic field, we can get induced torque. Okay. So the motor will continue to rotate because the torque is being produced. This is the cross field theory.